A look at section 2.2. This is the last section in chapter 2. Yes, these chapters are pretty short. We usually do just 2, maybe 3 sections of each chapter, so they go by pretty quick. So the working on like most of 3 chapters this week isn't quite as big as it looks like. So, but it's still a lot of work. Anyway, we're going to start off by organizing discrete data in tables. That goes by pretty quickly. We're going to look at histograms and what a histogram of discrete data looks like. Then we're going to jump over to continuous data and organize that in tables, and then take a look at histograms with continuous data. Then we're going to draw stem and leaf plots and identify shapes of distribution. Then we will be done with section 2.2. All right, so let's get started then. So here we have a bunch of raw data. It represents the number of available cars in a household based on a random sample of 50 households. So they polled 50 households, asked them how many cars do you have available, and then they just wrote it all down. Actually, it's US Census, but whatever. So here is all of it, and because it is countable things, remember, things that are countable are discrete. Somebody's not going to have 2.675 cars. And I guess you could kind of say one of them in disrepair, missing some pieces, could be, but let's not go there. Okay, so let's talk about a frequency table. So a frequency table, pretty easy. This is similar to what we did with the M&Ms in section 2.1. We just counted the number of people that had 0 cars, the number of them that had 1 car, the number with 2, 3, 4, and 5. You don't have to show me the tally marks, but the tally marks just kind of show that. So we have those tallied up, and then we have our frequency. And in order to get the relative frequency, we do the exact same thing that we did with the M&Ms. So I would do 4 divided by 50 because there are 50 total data values. And then we would get that the relative frequency is 0.08. Then we would do 13 divided by 50 and get 0.26, and go all the way down and get all of those values. So this would just give us the frequency of all of it. So basically 44% of households have 2 cars. So something I want to bring up here that is not in the PowerPoint, but it shows up in your homework, is cumulative relative frequency. So I'm going to add this right here, and sometimes I think things are self-explanatory based on the words used. I have learned that it is not necessarily self-explanatory, so I'm going to put this here. So the reason we would use cumulative relative frequency is I might say something like, what proportion of people have 3 or fewer cars, or something like that. The cumulative relative frequency will help you with that. So for example, in the first box I put 0.08. The second box would be 0.26 plus the 0.08, so it'd be 0.34. So I could say 34% of the people have 1 or fewer cars. And then we would take the 0.34 and add the 0.44, so I have 0.78. So I could say 78% of the people have 2 or fewer cars. So having this cumulative relative frequency helps you to just kind of at a glance see that 78% of the people polled had 2 or fewer cars. And it's just adding them as I go along. So I'm going to add the 0.14, so I get 0.82. Oops, that should be a 9.2. Apparently my mental math skills are a little bit off here. 0.92, then add the 0.06 to the 0.92, 0.98, and then this of course is just 1. So obviously 100% of the people in that poll or in that census have 5 or fewer cars. 98% of the people have 4 or fewer cars, and it's just really easy to take a look and see that really quickly looking at that cumulative relative frequency. Right, let's move on. So a histogram. A histogram is very similar to a bar graph, and with discrete values, it's almost exactly like a bar graph. It's just slightly different. And when it comes to continuous data, there are a couple of more differences, but with discrete data, it's almost exactly a bar graph, just some slight different things. So the height of each rectangle is the frequency or relative frequency of the class. That is the same thing as a bar graph. Each of our bars, we call it a class or category or bin. Bin is another word that we use. So those are three different words: class, category, or bin. Class is what you will see most. When I learned stats, I learned bins, and so that's what comes out of my mouth most of the time. They all mean the same thing. The width of each rectangle is the same. So all the rectangles are going to have the same width. And here's the difference between the histogram and the bar graph. The rectangles touch each other. So they're going to touch each other. So it's going to be a bar graph where they touch each other. So once again, excuse me. So once again, here's my frequency and relative frequencies, relative frequency tables for the number of cars available in each household. So now I'm going to put that into a histogram. So similar to a bar graph, each bar represents, the height of it represents how many cars or how many are in each column, how many each of these categories. But notice how my bars are touching each other. This is a histogram. And notice each of these numbers still is in the center of the bars. It's because that is exactly 4 cars. So here we have 3 people have exactly 4 cars. We have, it looks like 22 people have exactly 2 cars. So this is a histogram for discrete. We don't frequently use histograms for discrete. We usually use a bar graph, but I mean, you will see it occasionally, and it's not wrong. So it is just another way to represent your data visually. Moving on. Here is the relative frequency. So the graph looks exactly the same. However, instead of count on this side, we have our relative frequency. So it's showing the proportion of people that have that many cars. All right, let's move on. So classes or categories or bins, classes, categories, or bins. This is where we are grouped. So we are grouping things together. So when we're using continuous, we're going to group it together. We're going to have a range, and they're going to be the same. Each range is going to be the same distance between them. So when there's a large number of different discrete values, sometimes we will put them in a range. So let's say we're talking about the number of M&Ms that are in bags. That is still discrete, but you're not going to want to have, 40 different bars. You are going to want to have like a range. You'll say how many bags had like 5 to 10 M&Ms, how many of them, or 5 to 9 M&Ms, how many had 10 to 14. So when you have a large number of different values, you're going to want to, or when you have continuous, you're going to want to have intervals that make up several different values. You're going to have a range of values within each of your classes, each of your bars in your histogram. Whoops, that wasn't the right way to do that. There we go. So for example, here we go. So the following data represents the number of persons aged 25 to 64 who are currently work disabled. So this is the number in thousands, and so there are a lot of people. So I'm not going to do 1 for 25, 1 bin for 25, 1 for 26, 1 for 27. I'm not going to do 1 for each age. So here I have a range of ages. So our lower class limit, the words lower class limit refer to the bottom of our interval. So the lower value of our interval is our lower class limit. It is the smallest value within that class. That's our lowest class limit. So our lower class limit there of that first group is 25. The upper class limit is the largest value, within that class. So in that first group there, our upper class limit would be 34. So the range of the first bin of our first class goes from 25 to 34. And since 25 is part of it and 34 is part of it, there are 10 different values represented in there. That is our class width. We determine our class width by subtracting the lower class limit of the consecutive bins. So if I do 35 minus 25, I get 10. Do 45 minus 35, you get 10. Each of our bins, each of our classes should have the same width. They need to be the same size. That way we're comparing similar things. So make sure if you are creating a histogram that each of your class widths is the same. All right, so here we have a whole bunch of data. So this is a sample of 45 eruptions of the Old Faithful geyser in Wyoming. We're going to construct a frequency and relative frequency distribution of our data, and then we're going to make a histogram. So our smallest data value is 672 and our largest is 738. So when we are going to create a histogram, we will usually choose, now I think that they might use the word like convenient numbers or something. I usually say pretty numbers. I pick a nice pretty number near lower than the lowest, than our lowest value. Our lowest value is 672. I'm going to choose 670 because it is a nice pretty number that is just slightly lower than our lowest value. So I'm going to start my histogram at 670. I'm going to start my smallest class at 670. Now when you're making histograms in Excel, they automatically start with the lowest number. They will not choose a pretty number below that. I like to make it choose pretty numbers below that, and I'll show you how to do that in the lab video. But you don't have to. This is just something we do. It's just convention. It's just what we do. And so I'm going to use class widths of 10. So here's the classes that I'll have. 670 to 679, 680 to 689, 690 to 699, etc. And I need to make sure that my highest class contains the highest value. My highest value is 738, so that one does contain my highest value. So these are the bins that I'm going to have. So when you're choosing your bin width, choose it so that you have, usually we say like 6 to 12 bins. You don't want to have 50 bins. That is just way too many. And you don't want to have 3 bins. That's not enough. So make sure that when you're separating it, that your groupings, you have your groupings the right size to have like 6 to 12. Those are just rules of thumb. I mean, if you end up with 5, that's fine. If you end up with 13, that's 5. But just kind of a rule of thumb, we say be like 6 to 12 different bars in your histogram. Right, so here is my frequency table for with the bins that I have, the classes that I have. I counted how many values I had in each of these classes, and I created my frequency table. And this is going to make it really easy to make my histogram. And then I made my relative frequency also, just in case I want to do a relative frequency histogram. So just grabbing one at random, you can see 20% of my eruptions of the Old Faithful geyser are between 700 and 709. All right. So let's say that I decided to make my bins 5 instead of 10. I just decided I wanted them to be 5 instead because I want it to give me a better visual of my numbers. Notice how I have this big gap right here of 3 bins in a row with no values in them. That just makes your histogram ugly and awkward. We usually want to avoid having an ugly, awkward histogram. So if when you make your bins you end up with this big gap in the middle like that, we usually will make the bins a little bit bigger so that we don't end up with a big gap like that. So having the class width of 10 is better than having that class width of 5 where we have this big awkward gap in the middle. Plus, look how many we have. This is a whole lot. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. 14 is a little much. I mean, if every one of our classes had stuff in it, it wouldn't be as bad. But I definitely don't want 14 different bars and having 3 of them empty. It's just going to look ugly. You'll see in a second here. So, once again, so when I'm choosing my lower class limit, you choose a small observation, the smallest observation you're going to use. You're going to look at it and choose, it says convenient number, a convenient number slightly lower. I like to say pretty number, so choose a number that's pretty, that's just a little bit lower than your lowest one, and make sure that you go up higher than your highest one. I do not do this. You may do this if you want. Sometimes people will decide how many classes they want. They will choose a value and say, oh, I want 15 classes. And they will take their largest data value, subtract their smallest data value, and then divide by that number to determine their class width. To me, that's just awkward. I don't want to do that. I just really don't like, I would rather say choose a class width of 5 or choose a class width of 10 rather than deciding how many classes I want and dividing. I mean, I could do that here. Say my smallest number is 672. My largest is, so I do 738 minus 672. And then say, let's say I want, for some reason, I want 12 classes. Let me get my handy dandy calculator out here. And I could say, okay, that's 738 minus 672. That's 66 divided by 12. That gives me 5.5. So I would need to make my class widths 5.5. See how awkward that is? To me, it's just easier to just decide the width rather than decide how many classes you want. All right. We'll get to those other histograms in a minute. We're going to look right now at Roth IRAs. So suppose you want to invest in a Roth IRA. Let me see. Are my histograms here? Okay, I'll go back to that. So here is my histogram for the Old Faithful eruptions. This is with the class width of 10. I still have one that's empty, but this isn't super ugly. I mean, it's not gorgeous, but it's not super ugly. It represents our data well, and there's just one empty bin. It's not too bad. Let's take a look with class width of 5. See how we have that big, huge gap in there? I don't know why. Oh, there's just no numbers on them. So 685 would be here, and then this would be 695. So I have these 3 bins here that are empty, and it's just crowded. It's just not as nice. So a lot of stats, a lot of the visual representations, a lot of the rules when it comes to that, it's just kind of common sense stuff, and that's kind of how it is with making your histograms. When you're making them pretty, it's just a common sense thing. This one right here looks a little bit better than this one, and it's just kind of a common sense thing. One thing that you'll hear me say over and over is statisticians don't deal in absolutes. We use a lot of adverbs where we'll say something like mostly, it is mostly, you know, I don't know, mostly bell-shaped, or and we use a lot of words that make it sound like it's not exact. We don't use exact things. We don't say something is exactly this way. We don't say something, we'll say something is mostly true, or I don't know, you'll see. You will see as we move on that we do not deal in absolutes. And this is kind of because stats is a science, and just like in science where we don't say we've proven anything, we say things a theory. And if something is a theory, it's basically proven, but it just leaves room for further experimentation. Okay, let's move on. So here I am, back to my, I'm investing in a Roth IRA. So here, this table, this right here is the 5-year rate of return in percent adjusted for sales charge for simple random sample of 40 mutual funds. So these are the interest rates of mutual funds. A lot of really beautiful beautiful decimals here. Don't worry, you don't have to like copy all these down. we're going to construct a frequency distribution of the data. So here we go. So I decided to make my bin width on these ones. I made them 1%. So one goes to 8, from 8 to 8.99, 9 to 9.99, and all the way down. So notice, so I'm 2 decimals on my interest rates, so I go to 2 decimals here. You need to make sure that you are saying 8.99 because we went to 2 decimals on the other. So I have my frequency and I have my relative frequency. So I'm going to go further. This is a lovely histogram created by Excel. I didn't put labels. This would be frequency. This would be rate. And then whatever Roth IRA, rate of return. So in this case, Excel decided how it was going to create this. It came up with all of it. I don't like the way Excel does it on its own. I'm going to show you some ways when we go into Excel to make this look a little bit prettier. If you were doing it by hand, it would look a little bit more like this. And I want to show you, so the only numbers on here are the upper limits. So these are the upper limits of each of these classes. We're not showing the lower limit. We're showing the upper limit of each of these classes. Okay, let's go talk about stem and leaf plots. So I'm not the biggest fan of stem and leaf plots. You will not be required to do anything with stem and leaf plots on the test, but they are in your homework, which is why I'm teaching them. I haven't found stem and leaf plots extremely useful. I guess if you want to make sure all of your data shows up and you're looking at the shape of the distribution, you probably would use it, but I have not found them extremely useful. But it is something that is in our curriculum, it is something that is required to be taught, and it's in your homework. But once again, it will not be tested. So as long as you can get through your homework, you are okay. So I'm going to use, so when we are making a stem and leaf plot, you have something called a stem. So the stem looks just like a line. And on the left-hand side will be all of the numbers except the last digit. So for example, if I had a data value of 147, 1 and 4 would be right here. That would be part of my stem. And then 7 would be over here. That would be the leaf. If I had 184, I'd have 1/8 there, and then 4 would be here. I'm going to show you how to make one, and I'm going to show you what they look like with the data sets that we already have for this lesson, and hopefully it'll make sense. Okay, so we're going to take a look at our geyser eruptions, and then we are going to take a look at our at the interest rates. So first off, this is for the geyser eruptions. This right here, these are the stems. These are the stems. The reason I have 72 twice here is because there's a lot of values with 72 in my first two for my hundredths and tenths place. There's a lot of values there, so I split them up. So I'm going to do 0 through 4 on 72 on the top one, and then 5 through 9 on the second one. So I'm going to go through, I'm going to put them disorganized first, and then we will redo this in an organized fashion. So first I'm just going to list them all out. So my first value was 728, so I just put an 8 there. My second value was 730, so I'm going to put a 0 there. Third value is 726, put a 6 here, and I'm just going to go through and do all of these really fast because I don't want to talk through all of it. Oops, hold on here. This is the raw stuff, okay. So I'm just going to put these here as they show up. Oh, it decided to change to black. 8959655. So this is still disorganized. This is still practically just raw data. This is not the final product. This is just me writing down all of the values, and I'm going to organize them in a second. 86956233685. Okay, so this is still disorganized. This should be a 1, not a 5. Okay. I'm going to change my color, and I'm going to make the final stem and leaf plot over here. Once again, we have 67, 68, 69, 70, 71, 72, 72, and 73. So your final stem and leaf plot, I'm going to put another color just because it's fun. Your final stem and leaf plot will have the leaves in order smallest to largest. They will be smallest to largest. So instead of 8, 2, this would be 2, 8. We don't have any 68s. I need to make sure every value is in there, but from largest or smallest to largest. So it will look like this. So every value in 690, all of the values are represented from smallest to largest. And then this one would be 0, 0, 2, 3, 6, 8. So I have 700, 700, 702, 703, 706, and 708. And remember here, oh wait, so these are just smallest to largest, all the values represented. Remember, I'm only doing up to 4 here, and then I'm going to do 5 through 9 here. That's not the right number. Sometimes it's hard to talk and write at the same time. 6, 6, 8, 9. And then 0, 1, 2, 3, 3, 3, 5, 5, 6, 8. There we go. So this right here is your final stem and leaf plot. Make sure that you label it, and you would have to have a key on here. So when you're making a stem and leaf plot, you would do something like this. You would say 72, 5 equals 725. You would have to have a key on there. And then you would put your title up here, like time between eruptions. So, but make sure you have that key on there. That key is important. And you are not going to have to make one for yourself, but you will be answering some questions about them in your homework. All right, let's move on. So once again, we're going to take a look at something with a decimal. So these right here are the unemployment rates. I don't know what year this is, but these were at some point in time the unemployment rates in all of the 50 states. I'm going to do a stem and leaf plot with these, and I'm not going to write it all out because that takes forever. But one thing important here, when you are using a decimal with a stem and leaf plot, the whole number part is your stem, and then your decimal is going to be your leaf. Let me show you what that looks like. So right here is all of my, these were all of the unemployment rates. And then I would say something like 4.7 equals 4.7. This would be my key. So the decimal is the leaf, and the whole number is the stem. So I'm sorry, I mean, I'm really excited about the math I teach. I love this class. I love this math. But stem and leaf plots do not get me excited at all. I'm not super happy about them being part of it. They don't seem super useful, but they must be useful in some way, somewhere. Otherwise, they wouldn't remain in the curriculum over and over. And they are in the AP Stats stuff that I teach at the high school. All right. Oh, this was the disorganized. This is the organized. I should put this back here. So 4.7 equals 4.7. And it doesn't matter which data value you use for your key. Just pick one. All right, this is the organized. Everything is smallest to largest. Organized, all nice and pretty. Right, and that's all I'm giving you for stem and leaf plots. If you're confused, make sure to post in the discussion board or send me a message, and I'll try to help you through it. All right. Shape of distribution. This is something important. This is something we will be dealing with for a while. It does not go away. It is important. So sometimes when we're talking about a variable, we'll describe it by talking about the shape of its distribution. So when we make a graph of it or any kind of visual display, we will talk about how it is distributed. And there's definitely some keywords that we use in order to describe those shapes. So first, this right here is called a uniform distribution. So it is symmetric, which means that if I folded it in half right at the middle, it's going to land right on top of it. It's going to look the same on both sides of that half. But it is evenly spread across. It's a nice pretty rectangle. Now sometimes one could be slightly higher. So you could say roughly uniform, mostly uniform. This is that whole we don't deal in absolutes. Like let's say this bar right here was just slightly higher than the rest of them. So this is still mostly uniform. It's still roughly uniform. It's not another shape just because it has this one little thing. So this is when the adverbs come in, where we would say this is roughly uniform distribution. Roughly symmetric. Next we have a bell-shaped. The bell-shaped curve is something we're going to be dealing with a lot. We will be dealing with this from now until the end of this term. So our bell-shaped distribution, the highest frequency is in the middle, and then they tail off to the left and right. So if I drew a nice little curve over there, it's kind of shaped like a bell. So we call this bell-shaped. We also call it normal, and it is symmetric. If I folded it in half along here, that's a nice pretty straight line, it would land basically right on top of each other. Sometimes we'll say something is roughly bell-shaped or mostly bell-shaped. People understand that, and it is absolutely okay. So when it's shaped like a bell like that, this is a bell-shaped distribution. All right, this one right here is called skewed right. It's exactly the opposite of what you think it would be. So if it has a longer tail over here on the right than it does on the left, it is considered skewed right. So when you have that long tail on the right, it is skewed right. Also, if it has the tail over here on the left, it is skewed left. So when you have that long tail out there, so most of your data is over here on the right, you have the big old peak up here, and you have your tail out here, this is skewed left. All right, so let's talk about the different distributions. This one right here, think about this, think about it, get an idea in your head. What is the shape of this distribution? If you said that it was bell-shaped, ding, 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 you are absolutely correct. It is not exactly bell-shaped, but it is roughly bell-shaped. It's mostly bell-shaped. Because, I mean, this one right here is a little bit smaller than this one right here, but this is still considered bell-shaped. How about this one right here? Our tail is on the right, so this is skewed right. If you said skewed right, you are correct. All right, next one. This one right here, it is skewed left. Our tail is over here on the left, so it is skewed left. I bet you didn't think that you'd have to know your right and left really clear in this class. Finally, this one's kind of cheating because it's right down here. Pretend you didn't see that. This is a uniform distribution. So it is a nice, pretty rectangle. So this is all for 2.2. Make sure if you have any questions, you post in the discussion forum so that your classmates can help you and I can help you, or you send me a message and I will make sure to check messages frequently. That is all. Have a great day.